Are you ready to dive into the depths of the outer solar system and explore the mysteries of the iced giant Neptune? The first real images of this distant planet have been captured, revealing stunning details and surprising discoveries. Join us on a journey through the swirling clouds and icy moons of Neptune, and discover what these images can tell us about the evolution of our solar system. Don't miss out on this epic adventure. Watch now, and let's explore the wonders of Neptune together. What is Neptune? Neptune is the eighth and farthest known planet in our solar system. It is a gas giant, similar in structure to Jupiter and Saturn, with a thick atmosphere primarily composed of hydrogen and helium, as well as trace amounts of methane, water, and ammonia. Neptune is also known for its beautiful blue color, which is due to the presence of methane gas in its atmosphere. It is the fourth largest planet in the solar system by diameter, and the third largest by mass, and has a very strong magnetic field that is tilted at an angle of about 47 degrees from its axis of rotation. Neptune was first discovered in 1846 by astronomers Urbain Le Verrier, John Couch Adams, and Johann Galle, using mathematical calculations based on perturbations in the orbit of Uranus. James Webb Space Telescope's findings. On September 21, 2022, the James Webb Space Telescope, JWST, turned its golden mirrors toward the iced giant Neptune. This planet, like its fraternal twin Uranus, is one of the least explored planets in our solar system, only briefly visited by Voyager 2 in 1989. Its extreme distance from Earth makes it extraordinarily difficult to study with even the world's largest telescopes, but efforts to study Neptune are well worth the investment. We know so little about ice giants that studies of the Neptune system are largely in the realm of pure scientific discovery. Each new thing we learn about Neptune makes a huge contribution to our understanding of it. Studying Neptune can also give us insights into worlds beyond the solar system. Our studies of planetary systems around other stars suggest that objects in the size range of Neptune are abundant throughout our galactic neighborhood. Until a mission is sent to study an ice giant up close, advances in understanding this important class of planets will rely crucially on JWST and other telescopes. And although JWST has only captured a brief glimpse of the Neptune system, we're already seeing just how much this powerful telescope might be able to tell us about the planet, its rings and moons, and potentially other similar worlds. Neptune with Triton. JWST Wide Field with Neptune in this image by JWST's near-infrared camera, NIRTM, you can see Neptune along with Triton, which appears as a bright blue object to Neptune's upper left. Triton is brighter than Neptune because its surface reflects 70% of the light that hits it. In the background, you can see a smattering of hundreds of galaxies. Welcome back to the Neptune system. In 1989, the Voyager 2 spacecraft delivered our best images to date of the Neptune system during a brief flyby. Voyager 2 revealed a planet with a dynamic atmosphere and a rich ring system. The flyby also demonstrated that Neptune's largest moon, Triton, harbored a complex surface and active cryovolcanoes that were resurfacing the moon's south polar region in real time. In the decades since Voyager, Neptune scientists have turned Earth's best ground and space-based telescopes toward this remote world. Its extreme distance, however, helped the planet keep its secrets close. JWST, with its exquisite infrared sensitivity, opens a new window into the Neptune system. The first JWST images of Neptune show myriad cloud features, the bright shine of Triton's icy surface, many of Neptune's moons, and its system of rings. P2NE from JWST annotated the Neptune system, imaged by JWST in 2022. The main ring components are labeled on the right and various moons are identified throughout the system. The murkiness around the planet is scattered light from the planet and its bright cloud features. Neptune's clumpy rings. The ring system was the surprise breakout star of the JWST Neptune images. In recent decades, our largest telescopes had only been able to image the densest parts of Neptune's rings, and only barely. JWST's first images contain a great deal of information about the ring set, including important details that we can tease out by looking at the source frames. The first detections of Neptune's rings, like those of Uranus, came from occultations. Astronomers monitored a star as the Neptune system passed in front of it and looked for a telltale blink of the star as a ring blocked the starlight. Oddly though, sometimes there were blinks that seemed to come from rings, yet at other planetary science community about what this might mean. Mistakes in the occultation analyses. Partial rings, Voyager resolved the riddle of the rings when it imaged the complete Neptune system. The ring system was indeed complete, but certain regions were distinctly thicker and brighter within the bright outermost Adam's ring, named, like all of Neptune's rings, after an astronomer who played a crucial role in the planet's discovery. These clumps or arcs orbit around the planet like moons, and therefore appear at different places at different times. Hence, occultations could sometimes detect them, but not at other times. Mystery solved. Subsequent attempts to directly image the Neptune ring system were occasionally successful for the densest arcs, but the fainter dust sheets were beyond the grasp of even the most powerful telescopes. The diffuse Gao ring closest to the planet is Neptune's faintest ring. The next ring from the planet is the crisply defined Leverrier ring, which is a bright inner edge to the wider and more diffuse Lassell ring. The outer edge of the Lassell ring is called the Arago ring. Enter the newest JWST images. Even in these short exposures, the entire Neptune ring system pop right out. These amazing images are due to the exquisite sensitivity of JWST's cameras, combined with the remarkable stability of its mirrors. Together, these qualities permit the detection of extremely faint structures next to extremely bright objects. See also the JWST image of the rings of Jupiter, which are detected despite being 1,000,000 times fainter than the nearby disk of the planet. Astonishing activity in the atmosphere of Neptune. JWST's near-infrared viewing powers allow us to examine different levels of Neptune's atmosphere because of the nature of the molecule methane, which gives both of the ice giants' atmospheres their distinctive bluish color. Methane absorbs light differently at various wavelengths. By selecting wavelengths of light that aren't absorbed by methane, JWST can peer into deeper levels of the atmosphere. This also allows JWST to identify high-altitude clouds that scatter sunlight before it is absorbed by the methane below. Neptune's poles. A major feature that can be seen in all filters is the South Polar Feature, SPF, which is not located at Neptune's south pole, but instead circles it at a latitude of about -70 degrees. It was first reported in 1989 when Voyager 2 did its flyby and has been a persistent feature at Neptune ever since. The SPF is a clump of clouds, so condensed that it usually appears as one feature in most images. In one of the JWST filters, at 300 down at 3 microns, the SPF is so bright that it caused the only instance of saturation in the Neptune campaign. This saturation can be seen as a black dot in the center of the feature. With the sensitivity of JWST, we can resolve the separate clouds that make up this feature. JWST detected other structures at the South Pole as well. At 2.1 microns, f210 m, JWST saw a bright polar vortex that had been observed in the past, as well as a bright continuous band surrounding the pole that had not been detected before. Not because we didn't have the sensitivity, but because it had not been there in the past. The band is around the same brightness as the polar vortex, so if it had existed when the polar vortex was observed, it would have been spotted as well. Neptune specialists are excited to continue observations of this new feature and the others accessible by JWST. Neptune's many moons. In JWST's wide-field image of Neptune, you can see its largest moon, Triton. Triton's odd retrograde, backwards, and tilted orbit lead planetary scientists to speculate that this object is not a native moon of Neptune. Rather, Triton is likely a Kuiper belt object, like Pluto, that strayed just a little too close to Neptune sometime in the distant past and was captured by the ice giant's strong gravitational field. Future JWST observations will focus on a detailed examination of the infrared colors of Triton. We hope to learn more about its surface composition, its thin atmosphere, and how it compares to other large Kuiper belt objects, such as Pluto, Eris, Makemake, Haumea, and others that JWST will observe. Triton aside, at least 6 other known moons of Neptune are definitively detected in the JWST images. Despina and Galatea are embedded within the rings and are thought to be responsible for helping to craft the detailed ring structure. Naiad and Thalassa are found within the inner, dustier parts of the ring system. External to the rings, the moons Proteus and Larissa can be easily detected.